Okay, so we'll look at the AVL tree, and our goal is to get the sublinear time on all of our operations. So first off, just some background on the AVL tree. So the AVL tree is actually named after its inventors, Edelson, Velsky, and Landis. So unlike some of our other algorithms and things that you can't exactly reason out anything about the behavior based on the name. So selection sort and insertion sort, the name of the sort gives some indication about how it behaves. So you'll notice over here in the Wikipedia article, it gives details about the time complexities. So the search time, the insert time, and the delete time all do end up being logarithmic. So our sublinear times that we're going for. So now let's take a look at the mechanics of how we can do that. Okay, so first of all, AVL trees have some properties. First and foremost, they've got a shape property. It's a binary tree, so we've already talked about binary trees with heaps, and with binary search trees, of course. There's a balance constraint as well, and what this does is it restricts the height of subtrees. So subtrees can differ in height by no more than one. So subtrees are nearly balanced. They're not perfectly balanced, but they have to be very nearly balanced. They also have an order property, which is the same order property that we had in binary search trees, that basically a node's left subtree will have keys that are less than the node's keys, and the particular node's keys will be less than everything in its right subtree. Okay, so just kind of a quick tree term review. So trees can be thought of recursively. So we can think of this tree over here on the right as being a node with two subtrees. Okay? And earlier in the semester, we also talked about the concept of height as a property of an entire tree. But since we can think of trees recursively, we can also think of the property of the height property of a particular subtree. So just kind of a review, that the definition we used for height, that's the maximum number of links from a particular node, the root, when we were talking about the whole tree, to its descendant. So conceptually, I mean, the height is the height. When we draw out the diagram, the height is kind of proportional to the number of links from top to bottom. Okay, so in this unit, we're concerned about balancing subtrees, and we're interested in the subtree height. So the height of a subtree at a particular node. So this is a property of a particular subtree. A subtree will be one taller than its tallest child. So what I mean by that is we can actually figure out the height of a particular subtree. So if I'm interested in the tree starting at A, I can think of the two subtrees to its left and its right, and A's height will be one taller than whichever of those subtrees is the tallest. So just as kind of a more abstract diagram, maybe I've got a short subtree and a tall subtree in a particular node. So maybe this is the subtree on the left is height 1, the subtree on the right I'm referring as height subscript 2, where the height subscript 2 is the taller of the two. So the height at my root node here will be, in this example, the height of tree h under subscript 2 plus 1 above that. Okay, anyway, the convenient part about this is we have an easy formula to figure out a particular node's height if we already have the height of its subtree. So just as kind of a practice, let's look at this little example problem and think about the heights of the various nodes in this example problem. This would be a good spot to pause the video and think about the heights of the various nodes. By the way, I've kind of shown a node here, N5, is kind of grayed out to indicate that this node doesn't exist. So let's also think about the concept of height as it relates to non-existent nodes. Okay, so node 1 will have a height, so we have a path of 1 down to its left, and we have a path of 2 links down to its right. So the maximum of those two is 2. So it'll have a height of 2. Node 2 has nothing below it, so we could think of its height as being 0. Node 3 has 1 link down to its left and nothing down to its right, so we could think of its height as being the maximum of those, or 1. Node 4 we could think of as having a height of 0. Now just to extend this, we kind of think of a node with no children as having a height of 0. So we could think of the non-existent node as having a height of -1. Okay, that may make it easier to do some of our analysis and discussions. There are other ways to think about this where you could change your representation of height or focus on the concept of balance rather than height, but sometimes it's convenient to think of non-existent nodes as having a height of -1. Okay, so our goal in building and working with AVL trees is maintaining these properties. And we're going to do that incrementally, and that's really, really important. So basically what we're going to do is we're going to focus on our operations, like the insert, and we'll start with the binary search tree insert that we've already worked with. So that binary search tree insert takes care of two things. It makes sure that new nodes are added in the proper order, and it also ensures that we've still got a binary search tree. So that's kind of two of the three things that we need to maintain for our AVL tree. So the third thing we need to maintain is this idea of balance. But the insert will definitely add a new leaf node. And doing that may cause the height of a subtree to grow, and consequently it may, not always, but may break the balance constraint. Our other operation that changes the shape of the tree is the remove, and it'll, of course, remove a node. We will again start with our binary search tree remove, which will maintain the binary search tree shape. And just like with insert, it may actually end up deleting a leaf, which may change the height of some subtrees and may consequently break the balance constraint. Okay, so again, we are going to maintain this balance property incrementally. And we're going to assume that before we do an insert or remove, the tree already has maintained the balance constraint, and we can consider it to be balanced in terms of the AVL tree. So both the insert and the remove may change the height by exactly one node. The insert will add a new leaf. The remove may end up removing a leaf. But that's just one node, so at most we're changing the height by 1. So the tree may be off balance by 1 level. Okay, instead of having a difference of height of 1, some subtrees may have a difference in height of 2. Okay, let's define this idea of a node's balance. So node's balance we can think of with the difference in height between the left tree and the right tree. So take the left tree's height and subtract off the right tree's height. So first off, if these two are equal, I'm going to draw kind of a little picture here of a subtree and a subtree that we would think of as having the same height, so the same total up and down, and a particular node. So if they're equal, that will be 0. That kind of represents balanced subtrees. On the other hand, if our left subtree is taller than our right subtree, when we do this subtraction, we'll end up subtracting a small number from a larger number, and we'll end up with a positive result. So a positive result means that our tree is left-leaning. Then we've got the complement of that, where we've got kind of a tall subtree on the right and a shorter subtree on the left and a root node. And if we do the subtraction, we'll end up with a negative number, which means we're leaning to the right. Okay, so remember our subtree constraint is that the height of the left and right can differ by 1 at most. So if our difference is plus or minus 1, or if it's 0, that's okay for an AVL tree. However, if it's greater than plus or minus 1, that's invalid. And remember that we're doing things incrementally, so it'll never be off by 1 more. So typically when we experience an unbalanced problem in our tree, it's off by 2 instead of just by 1. So what's really handy about this is we can focus on things that will change and correct this by just 1 unit. So if we're off by 2 and we can somehow change it to be off by 1 or off by 0, then our tree is rebalanced. Okay, so for our discussion on balancing, I'm going to focus on just insertion, but everything we're doing will be able to generalize to remove. So insertion adds a new leaf. So again, that could increase the height of the tree. So that new leaf all by itself, it has no children. So we would think of the left child and the right child possibly as having a height of -1 each, and those are equal. So this new node is all by itself balanced. When we insert a new node, the new node itself is just fine. We don't have to worry about it. Okay, let's think about where in the tree we may have issues. Okay, so let's consider the parent. So it was balanced before we did the insert. And we've really got kind of 4 different cases for inserting a leaf that we're concerned about right now. So it's possible that we inserted some new node to the left of the parent. Maybe the parent didn't have a right child. Maybe the parent does have a right child. We don't really care what its key is. Maybe we inserted to the right of the parent and the parent didn't have a left child, or maybe it did have a left child and we inserted to the right, and we, again, don't really care what the key of the left child is. So we've got these 4 different conditions. So again, I'm going to kind of go through and indicate the height of the left and right child on each of these. So height of 0 and -1, those differ by 1, that's fine. 0 and 0, -1 and 0, and 0 and 0. So in all these cases, the differences in the subtrees are 1. So everything's going to be balanced after we do the insert. So that's great. Okay, so let's go and consider what happens even further up the tree at essentially the grandparent. So it was, again, balanced before the insert. So after the insert, it may be leaning to the left and the insert was on the left. So it's possible that, that we started off with something like this. The grandparent is leaning slightly to the left. And afterwards, it's now doubly leaning to the left. And at this point, we've got a problem. So our new node's height is 0. Its parent has a height of 1. The thing to the right of the grandparent is empty, so I'm going to consider that a height of -1. And here, we've got a difference of 2 in our heights. We've got an imbalance. We're essentially leaning to the left. Okay. In terms of our balance property, we would take the 1 minus the -1, which gives us a 2. So again, we're leaning to the left. So that left-left leaning tree shows one example of a problem, but it turns out we can kind of generalize that and identify 4 different out-of-balance scenarios that are possible. So we've just seen the first of them, the left-left leaning tree, but there's also the mirror image of that, the right-right leaning tree. Okay. And we could also think about just moving one of these nodes around a little bit and still kind of going out of balance on the left, but instead of this new node being to the left of its parent, it could be to the right of its parent. So we've also got the left-right leaning, and then its mirror image, the right-left leaning. So this one where, again, the grandparent, the node that's out of balance, is leaning towards a left, and it, because of the insertion, is leaning towards its right, and then again, the mirror image of that. Okay, so remember that when we change the height of a node, that it could impact other nodes. So just to review, the height of a particular subtree is the maximum of its left subtree's height, its right subtree's height, and then add 1 to it. Any change in a subtree's height could impact all of its ancestors. So we have to think very, very carefully about that. So if we change the height of something, it may cause changes to move up the tree. So when we're talking about these things that go out of balance, it may affect an entire complicated tree instead of just the very bottom layer that we were just looking at. So I want to be more generic as we look at those 4 different cases. So I'm going to use some additional notation to describe those 4 different cases. So again, let's look at the insert. We'll focus on this idea of a left-left leaning tree, and I'm assuming it's out of balance. So again, it's leaning to the left, and it's leaning to the left because of an insert on the left. Okay, so I'm going to think of kind of having this out-of-balance node, the node that I'm really kind of interested in, the one where I can detect there's a problem, and the fact that it has at least 2 children. So I'm going to make this a little bit more generic, and I'm going to think of having subtrees that they may be empty, they may contain stuff. I don't really care. I'm just going to think of them as being subtrees attached to these 3 nodes of interest. So all of our discussions will really kind of focus on these 3 nodes of interest, starting from the one where we've detected the problem, and depending on which of its 2 children is higher, that'll be our second node of interest. And then from that node, we'll look at the taller of its 2 children to figure out where we're out of balance. So all of these can be detected based on height. Okay, so let's go ahead and look at the left leaning tree, and let's go ahead and apply some labels to it. So I'm going to think of the labels of the 3 nodes of interest as being A, B, and C, and I'm always going to label them in such a way that they're in order by their keys. A's key comes before B's key, which comes before C's key. I'm also going to label all of those subtrees in a similar fashion. I'm going to label them tree 1, tree 2, tree 3, and tree 4, such that tree 1's keys always come before tree 2's keys, and so on. Okay, so labeling. So with our left leaning tree, A comes before B, that comes before C. So again, I've chosen to call the bottommost node A here because of the ordering of its key, because it comes before B and because B comes before C. Then I'm just going to go ahead and label the subtrees. Basically, I'm labeling these from left to right, so or right to left. So A will have subtrees T1 and T2, B will have subtrees T3, and C will have a subtree T4. So these may be empty subtrees. They may be the insert case that we've already talked about, but this could be a more complicated tree with an out of balance condition higher up than the bottom level. So again, tree 1's keys all come before A. Tree 2's keys all come after A, but before B's keys, and so on and so forth. So these are just labeled in order. Okay, now we can actually start to think about operations we can do that will fix our out of balance condition. So I'm going to start with the left leaning tree. So we're going to restructure this tree. So to try and pull up the left side. So again, it's kind of leaning it too far this way. So if we think about our subtrees, we've got this T4 subtree, and we've got the imbalance conditions causing it to tilt to the left side. So somehow we would like to lift up on this left side and maybe push down on the right side to try and have some sort of a balance. So I'm going to go ahead and add in my subtrees here. And what we want to do is we want to both lift up the left side, push down the right side, and also continue to maintain our order property. So that's part of the reason I chose to label the nodes based on their ordering. So I'm going to go ahead and restructure these. And we know that A comes before B and B comes before C. So we can form a nice little triangle, A, B, and C. And then we can attach the subtrees in this order. So first off, let's make sure that our order is maintained. So tree 1 comes before A, and tree 2 comes after A. We've maintained exactly that. A is to the left of B, so it's before B. B is to the left of C, so we can kind of think of B as coming before C. We've maintained that with our little triangular structure here. Tree 4 comes after C. It's still there. Okay, tree 3 requires a little bit of careful thought. So it's after B, but because it's to the left of C, it's before C. So we've still maintained it as being to the right of B. So it's after B, but it's to the left of C, so it's still before C. Also, look what's happened here. Tree 4, which was the shorter of the two, has now been pushed down one level. Okay, we were leaning too far to the left, so either tree 1 or tree 2 was a little bit too tall, and we've essentially moved both of them up one level. So this ends up restoring our balance. We've kind of lifted up the tall side and pushed down the short side. And we've also maintained our order. Okay, let's look at our second condition, our right leaning tree. So again, I'm going to label my nodes A, B, and C. And notice that they're in different positions this time because the nodes are labeled based on their ordering. So in this case, A is the root. B is to its right, so it comes after A, and C is to the right of B. And again, I can attach my subtrees, and I'm just essentially kind of working from left to right here, but the subtrees are in an order as well. So tree 1 would have the keys that come first, tree 2 would be second, tree 3 and tree 4, which are mislabeled right now, would come next. There we go. Okay. So again, we're going to go ahead and restructure this and essentially pull up the right-hand side, the side that's a little bit too tall. And we can do the exact same trick that we just did. So basically, we can think of A, B, and C and maintain their order, and then maintain the order of the subtrees relative to A, B, and C. So again, I'm going to form the exact same sort of triangular structure here with A coming before B, B coming before C, and still maintain the subtrees. Okay, so again, let's kind of double check our thoughts here. So T1 is still to the left of A. We didn't change its position relative to anything else. 3 and 4 were connected directly to C. Those are unchanged. The one that's been juggled around a little bit is tree 2. So again, it's to the right of A, so it comes after A, but it's to the left of B, so it comes before B. So again, we're to the right of A, but we're also to the left of B. So we've maintained the relative order of everything in these subtrees. Okay, so continuing on, let's look at the left-right leaning tree. So looks like this. Again, I have relabeled my nodes to keep their relative order. So B comes after A comes before B, and B comes before C. Again, I'm going to attach the subtrees, just kind of working from left to right and numbering them. So everything in tree 1 comes before everything in tree 2 and also before A, and so on and so forth. Same trick as before. I can think of the 3 nodes that are involved where I've gone out of balance. I'm out of balance to C's left, and it's out of balance to the right. So I can focus on these 3 different nodes, restructure them in a way that will lift up the side that's too tall, the stuff to the left of C, and push down the stuff to the right. So again, I'm going to form my exact same little triangular structure, and I'm going to attach the subtrees. And again, notice that the stuff that was a little bit too tall over here has now basically all been moved up. Trees 2 and 3 have all been moved up 1 level. Okay, so you can take a second and kind of verify to yourself that tree 3 is connected in the right order, but most of the others are tree 2 and tree 3 are in the right order. They're both juggled around a little bit. Okay, so we've also got the complement of this, the right-left leaning tree. And again, we labeled the nodes so that they're labeled in the order based on their key. A comes first. So our final example here is the right-left leaning tree. So again, we've got kind of the 3 nodes involved, and this time the node that's out of balance would be labeled A. It comes first. Its right child is C, and its the left child of the right child is B. So again, we've kind of identified the direction of the out of balance by labeling these 3 nodes and labeling them based on their order of their keys. And then we attach the subtrees basically from left to right yet again. And yet again, we're going to go ahead and focus on pulling up the right side and maintaining the order of everything by forming one of these perfect little triangles and attaching the subtrees in a way that maintains the order of all of the keys appropriately. Okay, so following one of these rebalances, the node where we actually did the rebalance, it may have a different height. So we may have to recompute its height, and consequently, that may impact the height of everything above it in the tree. So we may have to traverse up the tree, updating heights, and equally importantly, rebalancing if needed. So as we traverse up the tree, if things are out of balance, we first adjust the balance, and then we'll recompute the height. So the good news is that this process of rebalancing, the generic approach that we've talked about, will work for both the insert and the remove operation. It doesn't really matter why the tree is out of balance, as long as it's only out of balance by 1 level, which happens with both insert and remove. This rebalancing process can actually restore balance. I just wanted to mention that the common term for these operations is called rotations. So the left-left and the right-right are referred to as single rotations. So you can kind of think of these 3 nodes as being kind of twisted, rotated to the right, or in the case of the right-right, these 3 nodes are being twisted, are rotated to the left. Okay, the right-left and left-right sorts of operations are referred to as double rotations. You can kind of think of our nodes A and B as being rotated to the left and then kind of consequently rotated to the right. Or in the case of the right-left, you can kind of think of B and C as being rotated to the right, and then the resulting subtree being rotated to the left. Last thing to mention, so in all of our cases, I've kind of indicated that we identify the out of order, out of balance condition at some node, and then we focus on its children and grandchildren. So if we're out of bounds, we're definitely leaning one way or the other. There's no question about the second layer down, the child node, and being able to identify it. But some cases you may encounter a situation where the third layer, the trees are equal size. And if you encounter that particular situation, it doesn't really matter which one you choose to be the third node in your restructuring. So there are some cases where choices may be slightly arbitrary.